Hello everyone, and welcome to this video on Stokes Theorem on curved manifolds using differential forms. Now this is part one because this will carry over three videos and the ideas contained will be spread across the three videos. So Stokes Theorem is one of the most fundamental results in differential geometry and mathematical physics. It generalizes classical theorems of vector calculus such as Green's theorem, the Divergence theorem, and the classical Stokes theorem in R3. And it generalizes these to the setting of a smooth oriented manifold, or to the setting of smooth oriented manifolds in general. So let's have a look. All right, now, just hide that. All right, so divergence theorem. So given vectors x and normal vector, unit normal vector, the divergence theorem in R3 from vector calculus is, and this is a normal to some surface. So in R3, Euclidean space, then the integral of divergence of x over a volume V is the integral of x dot with the normal vector, unit normal vector, and surface element ds over the boundary partial V. That's the boundary of this volume V here. So from an earlier video, we found that div x was the Hodge dual, this star here, Hodge dual composed of the flat operator acting on a vector x, and then the exterior derivative of that, and the Hodge dual in turn of that. All right, so, and we found that it was equal to this scalar here, all right, in the coordinates x, y, z of Euclidean space. And that led us to the differential line without the final Hodge star on the left here, the differential of the Hodge star composed of the flat operator acting on the vector x gave us this object here with the volume element in R3, in Euclidean R3. So notice there's no square root g metric term in the front there because that's just one. And that gave us div x times dv, volume element. Now, on the right-hand side, this one here, the integral over the boundary, partial v of x dot n hat surface element ds is the integral of this, the vector x, dotted with the unit normal vector, that, and the surface element ds. And writing that again and performing that calculation here, the basis vectors combine out. The inner product gives 1 for each, and we're left with the scalar p times n1 plus scalar q times n2 plus r times n3 and the surface element ds. Okay, so multiplying through by ds there, we have this thing here. And this n1, that's the unit component of the unit normal vector in the direction of x, times the surface element is just the same as p, the scalar, times dy wedged with dz. It gives us this. So this is our oriented surface element, dy wedged dz. And that's all of this is just the vector x flatted with the flat operator there, the flat operator, and then the Hodge dual of that. And remember the vector flatted, xb here, or x flat here, gives us a 1 form, and the Hodge dual of that in R3 Euclidean space gives us the 2 form, and hence the 2 form here. So this would have been p dx here, and the Hodge dual of that was dy wedged dz. Okay, and you can see all that in past videos. So this is an integral over a surface that is the boundary, denoted partial v, to the region V. All right. We're looking at Stokes theorem in classical three-dimensional Euclidean case. That's where we'll start in this series of 3 videos. Now, Hodge dual of x flat is the same as the Hodge dual composed of flat acting on the vector x. Those two things are the same. It's a 2 form which we will call omega. Omega is this object here. And from this 2 form, we can get the exterior derivative of the 2 form. Differential d acting on omega is d acting on that. And that gives us div x dv, okay, as we saw on the previous page. Now this in turn gives the integral over v of div x is the integral of x dot n ds over the boundary, partial v, and that's the same as d, the exterior derivative acting on the composition of the Hodge dual with the flat operator acting on x, and on the right hand side that's the Hodge dual composed of the flat operator acting on x, okay, and which is just Stokes theorem in differential form expression. So the integral over v of d omega is the integral of omega over the partial of v over the boundary of v. And on curved manifolds, all of this is going to be the case as well, as you'll see as we move on over the next couple of videos. All right, so a statement of Stokes theorem. Let M be an oriented n-dimensional smooth manifold with boundary partial M, and let omega, and I'm going to use M and partial M throughout the rest of this series, except maybe in one or two cases, the rest of this 3-video series. And let omega be an n-1 form on M, and so M is n-dimensional. Then Stokes theorem states that the integral d omega over M is the integral of omega over partial M. Okay, so manifold M, smooth manifold M, and partial M the boundary. All right, so and we'll look at an example shortly. So key features of the theorem: the differential operator D, the exterior derivative, replaces the divergence or curl from classical vector calculus. The integral over M reduces to an integral over the boundary partial M. We've seen that, the right-hand side of that equation with the integrals there. It holds for arbitrary smooth n-1 forms, omega, making it a highly general statement. And the so that's very interesting. Not just the three-dimensional Euclidean case, but it holds in general. And that's what we'll see over the next couple of videos. The orientation of partial M is induced by the orientation of M. All right. So just coming back here to the three-dimensional case, then omega would be the 2 form we saw earlier, and d omega would be back in 3 form, in 3 dimensions. All right, now geometric. Okay, so Stokes theorem tells us that the integral of the differential of a form over a region M is equal to the integral of the form itself over the boundary partial M. All right, so that's just Stokes theorem in words. All right, this is a natural extension of the fundamental theorem of calculus to higher dimensions, and it encodes the idea that the flux of a field escaping a region can be computed from local infinitesimal data. That's all the dx's, dy's, and dz's. Okay, looked at locally, and then integrated over the coordinate system involved. We'll see that in the next couple of videos. So on this last point, imagine a fluid or electromagnetic field represented by a differential form, e.g. a 2 form representing magnetic field lines. The flux of that field through a surface tells us how much of the field is flowing through the surface. But Stokes theorem tells us something remarkable. You don't have to integrate the field over the entire volume or surface from scratch, as we did in vector calculus. Instead, you can compute a local exterior derivative of the form, a kind of infinitesimal divergence, the dx's, dy's, all the rest of it, or du, dv's, excuse me, and integrate that over the region. We'll see how we do that. All right, so in other words, the integral of omega over the boundary, partial M, is the integral d omega over the whole manifold, or at least over the coordinate system, the manifold involved. Now this expresses a global quantity, so flux through the boundary, partial M, as the accumulation of local infinitesimal contributions. That's the values of d omega in M. Why is this powerful? It localizes a global computation. The boundary behavior can be inferred from what's happening inside. It reveals a deep unity between geometry and analysis. The topology of a region, its boundary, is linked to calculus, exterior derivative. And in physics, it underlies conservation laws. So, for example, Gauss's law, electric flux is equal to total charge, is a special case. All right, so in the last video, just prior to this one, we looked at the flux of the curl of the vector field. So here was our vector field F, and here its components were minus y, x, and 0 over the upper hemisphere of the unit sphere. So F pointing out here, our surface S, and our boundaries in black around here, not marked. So we found the corresponding one form to B if you use the flat operator on this. So F flat, you're going to get omega as you'll get a 1 form. Okay, so the basis vectors partial over partial x will be flattened to give you dx, same with dy. And these components are in there in Euclidean geometry. the contravariant and covariant components are the same, right? Because the metric term is 1 for all of it. I've shown you that in a previous video. Okay, we now take the exterior derivative of this. So we found, if you look in the past video, I'm not repeating it here, that d omega was 2x wedge dy. So please, it's the video prior to this. Have a look, and all this entire problem was worked in that video. As a vector calculus problem, it's quite long, but in the language of differential forms, it becomes the double integral of d omega s. It's the double integral over s of 2x wedge dy, so, which is 2 times the area of the unit disk. And I showed you how all that happened in the last video, which is 2 pi. All right. Because remember, the unit disk area is 1, and then we had the 2 factor there. But all of that was explained in the last video. So differential forms on a curved manifold, which will really be the subject of the next video, but I'll touch on it here. The exterior derivative D. The exterior derivative takes a k form omega and produces a k plus 1 form. So the exterior derivative is a map from the space of k forms on M to the space of k plus 1 forms on M. It satisfies d squared is 0, meaning d omega is 0. And locally, if omega is expressed as this object here, then d omega is just df wedged with all the other differentials of the coordinates all the way up to k, remember being a k form. So for example, a smooth orientable surface S with boundary partial S and a 1 form omega, Stokes law applies in this form here. All right, so let's have a look. So as an example, step 1, define the surface and its boundaries. Let S be the upper hemisphere of the unit sphere. There it is. S is a set of ordered triplets x, y, z that belong to R3, such that they follow the rule x squared plus y squared plus z squared is 1, where z is equal to greater than 0 because it's the upper hemisphere. And the boundary of partial S is the equator. So partial S is a set of triplets x, y, and 0 belong to R3, where they follow the rule x squared plus y squared equals 1. So it's the unit disk in the xy plane, which is circling the xy plane. With vector field x is y partial x plus y partial over partial z, so y 0, y, this is our example. And we'll compute both sides of Stokes theorem using a coordinate patch over the hemisphere. Let's choose coordinates uv belong to the disk contained in R2. So pulling it back to R2, with x of uv is u, y of uv is v, and z of uv is the square root of 1 minus x squared minus y squared. All right, so we're taking x, y, z and pulling it back to the disk, parameterizing in terms of coordinates uv. All right, so this is valid over the unit disk as a set of ordered pairs. uv belong to R2 such that u squared plus v squared is equal less than 1. That is, we view the hemisphere as a graph of this object here. Now we compute d omega, which is the exterior derivative of omega. So the corresponding 1 form is omega is y dx plus y dz. So omega is x flat. Remember the vector form on the previous page. So we flat that, we get omega this. Then d omega is, let's take the exterior derivative of this. So we get dy wedge dx plus dy wedge dz. And we can use the anti-symmetry on the first part here. So we get minus dx wedge dy plus dy wedge dz. And so d omega is minus dx wedge dy plus dy wedge dz. And this is R2 form on R2, which we will now pull back to the surface. So compute the pullback of d omega to the surface. So we'll compute phi star d omega in coordinates u, v, where phi of uv is the square root of 1 minus u squared minus v squared. All right, so we compute dx, dy, dz in terms of du, dv. Well, dx is du, dy is dv, and dz is partial z, partial u times du plus partial z, partial v, dv. Calculating that, we get this. Calculating this, we get that. And if you remember, because we're calculating from here, remember z was this, 1 minus u squared minus v squared here. All right, remember here z of uv is that object. x of uv is u, y of uv is v, z of uv is that. Okay, and so that becomes 1 minus u squared minus v squared. All right, so we go, and so putting those in, we get this one here, partial z, partial u, and partial z over partial v is this, and putting them together, we get dz is that. So compute the pullback of d omega, okay, under phi, which is that map I've mentioned earlier. Then d omega is repeating this again and substituting, so we phi star acting on d omega, so the pullback of d omega under phi is minus du wedge dv, remember, just substitute straight here, plus dv, all right, dy was just dv, wedged with dz, and of course dz is that, so substitute for dz and we get dv wedge dz is this object here, dv wedge of all that. There we go. And then collecting some terms and tidying it up, we get dv wedge dv is 0, dv wedge du is minus du wedge dv, and so we have dv wedge dz is that object, and so that implies that the pullback of d omega under phi is minus du wedge dv plus that object there, or the pullback of d omega under phi is this object, taking out the common factor of du wedge dv. Okay, now next step, so that's the pullback here. So we integrate d omega over the hemisphere, so we integrate over the disk d contained in R2, where u squared plus v squared is equal to less than 1. So we'll change that to polar coordinates, so we'll let u is r cos theta, v is r sine theta, r is 0 to 1, okay, unit disk, theta is 0 to 2 pi, du wedge dv becomes r dr wedge d theta. I've covered that in a previous video somewhere in the polar coordinates. All right, then the square root of that is just 1 minus r squared. U is r cos theta. So substitute into the pullback. So the pullback of d omega under phi then becomes r cos theta on that minus 1 times r dr wedge d theta. And the integral becomes integral s over s, the surface hemisphere, which is our manifold in this example, and the integral of the omega of that is the integral 0 to 2 pi, 0 to 1, this object r dr d theta. Just split the integral down because there's 2 terms in here. So that bit there plus that bit. All right, next bit over, we get the integral of that cos theta d theta times the integral 0 to 1 of this object here, minus the integral here times that integral there. And so we get the integral 0 to 2 pi cos theta d theta is 0. If you look at the terminals there, when you evaluate between 0 and 2 pi, you're going to get 0. Because this will become minus sine, and sine of 0 is 0, sine of 2 pi is 0. Here, the integral 0 to 2 pi d theta times the integral of that will give you, well, that'll give you 2 pi, and this will give you r squared on 2, so we get a half. And that is equal to pi, so the integral d omega of that is minus pi. All right. And next step, we're going to compute this bit here. It's minus because the minus there, sorry, because this bit here goes to 0 on the left, so we get minus pi. Now the integral of omega over the boundary, partial s, so parameterize partial s as a unit circle in the xy plane. So here's the unit circle parameterized as a curve here, cos theta, sine theta, phi. Theta is 0 to 2 pi, x is cos theta, y is sine theta, z is 0, dx is minus sine theta d theta, and dz is theta. So we get omega as y, dx plus y dz, remember, our one form, and that becomes sine theta times that object there, dx, plus here y is sine theta times dz is 0. Remember, we're at z equals 0 because we're in the xy plane. So we get minus sine theta squared d theta. Very good. And then the integral omega around the boundary, so that's minus the integral 0 to 2 pi sine squared theta d theta. If you plug that into some calculus software, you'll end up with minus pi. And so that shows that we have agreement with Stokes' theorem, as you'd expect. And so that the integral of omega on the boundary is equal to the integral of the exterior derivative of omega over the whole region, or the surface in this case. Left-hand integral is negative, which tells us the net circulation around the boundary partial S, which is the unit circle in the xy plane, is in the negative or clockwise direction. The surface integral S d omega, measures the total curl flux circulation density of the vector field through the surface S. So the circulation of the vector field around the boundary is explained by a net flux of curl through the surface bounded by the curve, which is exactly what Stokes theorem says. And you remember in the last video, it was more complicated because we had del or nabla cross f, and then we had all those calculations to do. And yet with differential forms, it just comes out a little bit more easily. It's a little bit cleaner, more elegant. All right, now a special case of divergence theorem on a curved manifold, and that's really going to be the focus of the next video. But if we take omega is x mu wedge dx mu here, and this looks odd, doesn't it? With the index down here, but it's just deliberate, just to follow the index convention. In the next video, I'm going to put it back, but just for the sake, if you've got one index up, then you must have one down. All right? So it's just to agree with the index convention. That's the only reason I've done it. The star here is the Hodge dual of this, where x is a vector field and Hodge dual of dx mu, it's the Hodge dual of a basis 1 form, and Stokes theorem reduces to this. Okay, so the Hodge dual of a 1 form, if you're in 3 dimensions, you'll get a 2 form. You'd expect this to be a 2 form here, and this is our 3 form over here. So you can sort of see how that works, but that'll be the focus of the next video. So where dV is, on curved manifolds, the square root of the absolute value of the metric, and then dxn is the volume element in whatever dimension you're in, whatever dimension n you're in. ds is the surface element on partial m, and mu is the normal to partial m. All right. Now this is the generalized divergence theorem in a curved space, and we'll start focusing on that is the subject of the next video. All right. Thank you very much for watching. I can return that now. Thank you. Return that. Thank you very much again for watching. I hope you found that useful, this whole video useful. If you do, please like it and subscribe, and I hope to see you in the next video soon, in part 2 and then part 3 of this short series. All right, once again, thank you very much. Take care, everyone, and I'll see you next time. All right, bye.